So as I say, this is about the interpretation of astronomical images. And the interesting thing is that many people who look at images don't necessarily appreciate various kinds of perspectives about them. And I want to highlight some of them now. So have you ever seen a beautiful picture of space, perhaps a nebula or a galaxy, and wondered if the colors are real or how big it appears in the sky? Many pictures of the cosmos seem abstract and removed from our daily experience. The irony is that pictures of space capture that which is most common and ubiquitous. It is our daily view of life here on Earth that affords us such a uniquely special view. You see, the problem is when looking at astrophotography, there are no people or easily identifiable references to orient oneself. Yes, the abstract form of a nebula can be beautiful without further consideration. But if you saw a picture of a person that was green, or they stood taller than a house, you would instantly reassess the information the picture was communicating. There's a similar skill set that can be applied to astrophotographs, and that is what I'd like to show. So with that in mind, join me on a journey through space and time and revel in the mysteries of the universe. We live in a world of images, and our digital lives rely on our ability to interpret them. It is a skill honed by countless hours in front of screens, big and small. However, some kinds of images, especially those that depict tremendous scales of size or time, defy our ability to easily interpret them. So all of the pictures that I'll show in this presentation, they were taken by me, with exception to some of the, well, you'll see there'll be labeled like HST pictures and things like that. These images were not chosen randomly. They exhibit what inspires the most commonly asked question. What are the sparkles or lines that are emanating from the stars? Some people think that they're put there for artistic reasons. Others don't question their appearance in photographs because it meets an expectation of what a star should look like based on drawings or cartoons. These patterns are indeed artifacts produced by certain telescope designs. Reflecting telescopes that use mirrors have structures that hold secondary mirrors or other instruments. These rods or vanes obstruct a small amount of light that the telescope collects, and through a process called diffraction, the light rays are scattered. These so-called diffraction spikes are not desirable, and some form of diffraction will always occur with any obstruction. The images so far were produced with this telescope. This is the Schulman Telescope, and it's the primary telescope at the UA Mount Lemmon Sky Center. This telescope is available to take pictures just like the ones that have been shown so far. You can see the vanes that support the secondary mirror. Notice how this image, produced with a telescope that uses only lenses, has no diffraction patterns. There are no obstructions to cause it. Most large telescopes use mirrors because it's not advantageous or even possible to build telescopes made only of glass lenses. This is why most professional images have diffraction patterns. On a more philosophical note, notice how the light of stars is spread into a spectrum of its colors. The diffraction of light into its component wavelengths is a primary way that most astronomical measurements are made. Even though these are artifacts, the fundamental information is literally encoded in these images. It's as if the universe wants us to discover the answers if we only look enough and ask the right questions. Scintillating diffraction patterns are only but a superficial element of astronomical images. There are much more deeper considerations of what is recorded in a picture. Typically, CCD cameras that are optimized for astrophotography are very sensitive and can record many tens of thousands of discrete brightness levels. Computer monitors, by comparison, only display 255 grayscale levels. An astrophotographer then must choose how to represent and render the data recorded in an image. This is a picture of a wonderful spiral galaxy, and although its splendor is recorded in the data, Those values are being rendered in its unstretched form, with the monitor only displaying the very few first 100 brightness levels. By changing the white and black points, more of the data can be visualized. Now we see a galaxy in the center with some spiral structure, as well as a few other galaxies in the background. Finally, by representing the data in a nonlinear way, the faintest values displayed are proportionally brighter than the other elements of the image where they were already bright. However, even more of the story of this field is revealed. Now we can see faint spiral arms as well as the tidal tails of other interacting galaxies. When looking at astrophotographs, keep in mind that the person who creates the image consciously decides this element of representation, as well as many others, as we will see. Blend in the color information, and the image takes on new dimensions of life. Notice how I chose to display the faintest and noisiest features as delicately hinted. This communicates that those features truly are difficult to see relative to the other elements of the image. The colors represented in astrophotography come in a few major variations. The images you've seen so far in this video all record the visible wavelengths of light. However, this is only a small fraction of the electromagnetic spectrum, and astronomers pursue the entire span of energies that can be detected with instrumentation. With regards to the light that we perceive with our eyes, even if looking through the largest telescopes in the world, the universe would not appear with the vibrant colors shown in the images like this. Our biology is simply not designed to detect these minuscule quantities of light. A full color image of visible light is created with a camera with filters that discriminate between reddish light, greenish light, and bluish light. These pictures are called broadband images, and when the images are assembled, the colors of light are mixed in a way that is analogous to what our brains do. So in a picture like this, I do not choose that this should be blue or this part be red. If your eyes were as sensitive as the camera that was used and you could expose for as long, this is approximately what you would see. Sometimes people ask if an image such as this is enhanced in terms of color. I take a different perspective and explain that it is our view of the universe with eyeballs that is diminished. If you look through any telescope in the world at an object like this, you would not see any color in this nebula. Yet red and blue wavelengths of light would truly be hitting your eye. In this sense, then, this picture isn't an enhancement, but instead a more accurate portrayal of reality. And these instruments then become our surrogate senses that allows us to understand the world around us. Another kind of color representation is done through narrowband imagery. This method captures light or specific wavelengths, which results in high contrast images of nebular features. However, this isn't a true color image because all of the other wavelengths of light are not included. Here's a broadband image of the Eagle Nebula with the very famous pillars of creation in the center. These pillars were made famous by the iconic Hubble Space Telescope picture of them. The HST picture is a narrowband image. Note the wavelengths used were one green part and two red bits. These were then mapped as red, green, and blue, resulting in a mapped narrowband image, which is an arbitrary color assignment. As you can see, the HST picture of the Eagle Nebula is of just a small portion of a much larger object. This leads us to the important ideas of resolution and field of view. When looking at an astrophotograph, each pixel of a sensor detects light from a very small patch of the sky. The size of this area on the sky determines the finest possible resolution of an image. So first, a quick review of angular dimensions. A degree, perhaps the size of your fingertip held at arm's length, can be divided into 60 arc minutes. The moon subtends roughly 1/2 of a degree on the sky, so it is approximately 30 arc minutes across. A crater on the moon might be several arc minutes in size. An arc minute can again be divided into 60 arc minutes. So a bump on a crater on the moon can be of this size. Taken together, the array of pixels determines the field of view. The HST picture of the pillars is only a few arc minutes in dimension, whereas the field of view of the picture from the Schulman telescope is 10 times larger, though this is still smaller than the diameter of the moon. However, something deceptive is at play here. Each pixel of the HST image sees a tiny 0.05 arcsecond squares of the sky, whereas a pixel in my image covers a tiny patch of sky 6 times larger. Before I show a one-to-one comparison, there are some important rules of thumb to know about optical astronomy. First, stars are so far away, they are not resolved and are truly points of light. However, as light passes through our atmosphere, the rays are deviated by small amounts. We live in an ocean of air, and our view of space from the ground is blurry. Typically, this blurriness smears images by 1 to 2 arc seconds. Now, we know enough to start interpreting images of all sorts. Let's begin with this wide field image of the region of sky near the Orion Nebula. This image was acquired with an astrograph that I think I'm going to show here. Oh, yeah. So that's the Orion Nebula, and there's the astrograph. Each pixel at the back of this telescope sees 5 arc seconds of the sky. Recall that stars are points, and the atmosphere blurs images by 2 arc seconds, which is smaller than 5. This means that the stars in this image look like little pixelated squares. The name for this situation is called being undersampled. Now, we overlay the region of sky captured with the Schulman telescope of the Orion Nebula and zoom in. Due to the increased scale, we can clearly see more details, and the stars are now blurred across many pixels. Finally, we can overlay the HST picture and see things at its intrinsic resolution. The stars are nearly pixel-like again and undersampled again. The fine details here are due more to the fact that the telescope is above the Earth's blurring atmosphere than it is due to the optics of HST. Did you notice that the HST picture is not a full-color picture? One giveaway is that most nebula that have glowing clouds of gas are pink or red. Other variations with multiple pastel hues are a good sign the image is composed of mapped colors. Another thing to consider is that we now have 2 images with stars that are undersampled, both the wide field image and the HST image. So how in general can you tell the difference? The easiest way to know is to look at the size of the features in each object. If they are large compared to the field of view, it's most likely a large or space-based telescope image. Wide field of view images will have small stars, but also small details. Finally, no matter what kind of astrophotograph you're looking at, the stars in the image will appear to vary in their size. Stars are points, but all telescopes, even the ones in space, create images in which light is spread out due to diffraction. The brighter the star, the more of the scattered starlight you see. So sizes of stars in a given image only signify brightness, not true dimensions. Take, for example, this wide field and deep image of Betelgeuse. This star actually fits on 1 pixel in the sensor, but the bright glow of scattered light can be seen to spill across hundreds of pixels. So let's use our skills to identify a few different types of images. First, we'll start with what might be kind of a tricky image. This is a broadband image of one of the most colorful regions of the sky. Basically, each nebula type is shown here. There's red emission from glowing hydrogen clouds near the star on the right, and more of it in the lower left corner. The top of the frame is dominated with bluish scattered light from dust. This is called a reflection nebula. Finally, dark clouds of dust obscure the view, except where they thin, and then they show golden hues, especially near Antares, which adds some of its own yellow-orange light. This is literally the palette of a large majority of diffuse nebulae. Can you tell if this was taken with a large telescope yielding a high-resolution image, or is this instead a wide-field image with undersampled stars and lower-resolution details? If you said that this was a wide-field image, you got it right. This is a 4 by 8 degree region of the sky. You can fit 64 moons in this field of view. Galaxies such as these are so far away that only our imaginations can span the distances. As such, when we look at galaxies, we see great averages of information. The combined light of stars and nebulae in other galaxies lends itself to low contrast details and colors, because many of these things are mixed together. For this reason, it is unusual to see mapped color images of galaxies, except perhaps for those that are our nearest neighbors. Here is a broadband image of M82 with an enhancement in the hydrogen alpha emission that corresponds to the color of the red filaments of gas being expelled from this starburst galaxy. The colors are the same without the enhancement, but by adding more signal for this particular feature, the added contrast makes the image more compelling. When mapped colors are employed, the result is obvious and can highlight structures of galaxies. Here, radio wavelengths of light are mapped as blue and trace cool molecular clouds of hydrogen gas, which show the skeleton of the galaxy. Here's a broadband image that I took of the same. This is a full color image of what is effectively a narrowband object. This is a dying star that has lost its outer layers of gas. Our own sun may eventually end its life billions of years from now in a similar way. The sphere of gas fluoresces this characteristic blue-green color due to small amounts of oxygen in the nebula. This process always yields this color, which is why the HST picture of the same is an example of a mapped color image with its expected extraordinary detail. Here's another image. Is this a mapped color image? How about the resolution? What kind of telescope likely generated this data? Well, this is definitely a mapped color image. And note that the details are quite large. The difficulty is that many images are not posted at their intrinsic resolution. Even an HST picture like this can look like something a small telescope can generate from the ground, but when the full image is shown, the image characteristics become obvious. Finally, how about this image? This is another mapped color image, but this time it really is a wide field image taken with a small telescope. While the colors and resolution of an astrophotograph are generally image attributes that can be seen directly, many other aspects of processing that take place to produce an image are not obvious. Certain kinds of digital processing leave characteristic artifacts or other telltale signs. However, the important idea is that images of space are not snapshots. Raw data is typically dark, colorless, and perhaps uninteresting. An astrophotograph, then, is the sum of hundreds of processing choices that are made to render the final image. Given the same data, different people will end up with different results. I'd like to highlight a tiny few such considerations to give a taste of what these decisions look like. When the initial raw data is displayed, it's possible to identify colors or details that are desirable to have represented in the final image. Many processing choices will blunt the effort or make it an unattainable goal. Seeing the final image in your mind and processing the data in small methodical steps helps to stay on course. In this image, each of these features was observed early in the data, and maintained with every subsequent step. CCD sensors produce linear data that exceeds a monitor's ability to display everything at once, and so nonlinear ways of displaying tonal variations are crucial. Without the use of high dynamic range algorithms, the interesting features of this galaxy could not be displayed. Note the inner disk with bluish tips and thin dust lanes, as well as the outer distortions in the galaxy's halo. In fact, these kinds of decisions are not unlike what Ansel Adams would make when he adjusted the tonal values of his images. What interested him was not what he saw in his camera, but instead what he pre-visualized in his mind as a final image. He would then dodge and burn his film to achieve his vision. With astrophotographs, typically these adjustments are applied globally, or if selectively, they are conditionally applied based on thresholds of brightness, color, or contrast. High contrast in particular is an image attribute that is preferred by both image makers and image viewers alike. There is an ancient evolutionary preference for high contrast, and this preference is shared cross-culturally. Adams, of course, knew this and played with it in his photography. The same lessons apply to astrophotography, but with some caveats. Take this image of the Trifid Nebula. Which version of it do you find most compelling? There's no right or wrong answer. These are simply different choices. However, there are consequences for the choices that are made, and that is something to be appreciated. If you didn't guess, my image is the one that's on the left. Although I could cater to the sugar high that contrast gives, I don't, because it comes with a cost. Light that filters through the clouds of dust has a subtle attenuation and depth that I feel is lost and flattened with the opaqueness that high contrast creates. To me, there exist truths in astrophysical objects, and I enjoy communicating as many as are captured in the data. For example, here are 3 images of the famous galaxy NGC 7331. This galaxy features wonderful dust lanes, and in its disk that reach all the way to the center. With particular processing choices, it's possible to display the dust lanes all the way to the core very clearly and distinctly. But to me, the cost is high. Galaxies truly are brighter in their centers compared to their outer disks. Maintaining this truth and at the same time showing as many dust lanes as possible, that's my style. This means that although I show the dust lanes, they are more difficult to see in the center due to the lack of contrast. But to me, this is exactly what I would expect when looking at something very, very bright. I process this galaxy to show what a high contrast version looks like on the right, but my actual processing result, the one I prefer, is the one on the left. I think it is much more natural looking. It better encompasses those elements that I'm looking to communicate. Okay, so I have to switch here. Here is a picture of what appears to be a relatively nondescript picture of space. But one of the very best astrophotographs ever taken was of an object hidden in the inky blackness of this field of view. In fact, to appreciate just how superlative this image is, we'll need to use some of the lessons we've learned in this video, as well as find our place in the universe. To travel to these large distances that we need to, light speed is necessary. Light, in a particular unit of time, travels a very particular distance. Take, for example, sunlight. It takes light from the sun 8 minutes once emitted from the sun to reach us here on the Earth. So we say the sun is 8 light minutes away. Now, if we use the all too terribly small Earth units to measure that distance, we come up with a number like 93 million miles. So light units are much more appropriate and convenient for measuring distances in space. Take the size of our solar system, and I'm going to be very generous and include the interesting parts of our solar system. It might be about 1 light day across. So it takes perhaps light 24 hours to go from one side of the solar system to the other. What I'd like to do is create a model that allows us to appreciate how far away the nearest stars are, how large our galaxy is, and where all these other galaxies are. So I'm going to use a penny to build this model. I'd like to squish our entire solar system down to the size of a penny. This means that the sun, the earth, comets, asteroids, everything you know and love is now squished into this little penny area. Now, a penny is a little bit more than 1 centimeter, but to make the numbers nice, let's just say that this centimeter is now the size of 1 light day. At this scale, we can imagine how far away the nearest star is. Its name is Alpha Centauri, and it's located 4 light years away. At this scale, 1 light day is 1 centimeter. So a light year is 365 centimeters, or more than 3 meters away. Alpha Centauri then is 4 times further, at more than 12 meters away at this scale that I'm building. Now, imagine you want to describe the size of our galaxy. You only really need 2 numbers. How many stars are in our galaxy? This is how many pennies I would need to build the galaxy in this model. And I also need to know another number, how large the galaxy is. That's going to tell me how much area I need to spread all of these pennies out. Well, our galaxy contains at least, and this is a low number, 200 billion stars, and it's no less than 100,000 light years across. So to build our penny galaxy, I'd need to begin with 200 billion pennies. If I had 200 billion pennies, I'd be a very happy guy. There are not that many coins in circulation in, for example, the US. So this is just in our imagination. I'd need to spread out these pennies then by some average distance from one another to represent, like stars in our galaxy. So let's say that this is maybe 2 light years from one another. Alpha Centauri was 4 light years away, but the average distance from star to star might be half of that. So at this scale, that's going to be 6 meters or 20 feet. If I really did do this, and this would take a very long time to accomplish, I would spread out these pennies 20 feet from one another until I exhaust all 200 billion of these pennies. Even with 1,000 people setting down 1 penny every few seconds nonstop, it would still take a decade to complete this project. But again, this is in our imagination. In this model, 1 light year is around 3 meters. So the galaxy would be 300,000 meters in diameter, which is 300 kilometers. The numbers I've given are all they're basically underestimates. So things are actually quite a bit larger. And this is just our galaxy. To show where other galaxies are, even if you make our solar system the size of a penny, the Earth itself just isn't large enough a place to create this model. And we're going to be going beyond here to see where other galaxies are. Our nearest neighbor, for example, is the Andromeda Galaxy, and it's located 2.5 million light years away. The Andromeda Galaxy spans this image of nearly 4 degrees of the sky. If you were over there looking back at us, this is how we might appear, though I'd like to think that we have, the better spiral arms. The stars you see in this picture are all in the foreground and part of our own galaxy. Zooming into the center reveals dust lanes that swirl all the way into the nucleus. Note that I wasn't too aggressive with the contrast in order to communicate the brilliance of the downtown galactic center. So we live on the outskirts of what's called the Virgo cluster of galaxies, the center of which is around 40 million light years away. And that is what this is a picture of. This is a wide field image of that part of the sky that contains thousands of galaxies, though they're hard to see at this scale. You can see some of them, though. If you look closely here in the bottom right, you can see some fuzzy patches here, and there are more, and they're very hard to see, admittedly, at this scale. But each of those is another galaxy. If I turn on kind of an annotated view of this field, you can see, just based on where the labels are, where all the galaxies are without zooming in. And one of the things I'd like you to notice is that there is a gradient of galaxies. It's obviously much more concentrated in the lower right than it is, say, in the upper left. So towards the lower right really is in the direction towards the center of the Virgo cluster. Now, one of the nice things is I have been fortunate enough in the course of my career in astrophotography to have been given the opportunity to take pictures of many of these galaxies in this part of the sky. And I'd like to show you some of these pictures. Now, this is the part that gets tricky. Let's see if this works. I'm going to pause it here and just point out what should be the first one I'm going to show you. Right here, that little round blob, that is a beautiful spiral galaxy. That's M100. And when shown, at a much larger resolution anyway, you can really see that it's a beautiful face-on spiral galaxy, perhaps one of the very best in the Virgo cluster, as it happens. Another set of galaxies, let me see if I can pause it here, is down here in the lower left. This is M60. It's actually a pair. It looks like a little binary set of galaxies. And there is a nice picture of them. And a galaxy which is right here, I think is or is it this one? I think it's an overlooked galaxy. It's M58, which I just think people overlook. It's a beautiful spiral galaxy in the Virgo cluster. There are also galaxies of, let me just pause it when it comes up here, M91 and M88, and those are these two right here. What is interesting about the galaxies that I've just shown is that all of the spirals that I just showed you were along kind of this dimension of the Virgo cluster. They weren't down here. They were away from the center, more towards the peripheral part of the cluster. And that is not a coincidence, because as galaxies are more densely close to one another, they orbit each other more strongly gravitationally, and they mess one another up. You tend to have more elliptical galaxies in the centers of clusters of galaxies because they may have collided with one another or disturbed their spiral patterns. So you need to be in the outskirts of a cluster for your spiral countenance to kind of survive. So that's why we're seeing all the spirals kind of out here, whereas mostly elliptical galaxies more towards the center of the Virgo cluster. And it is there that I really want to go. The whole reason for this picture and all of the explanations that I've given so far is that I'd like to journey to this one. This is M87, and it harbors a monster. It is amazing. And I believe it has basically the best astrophotograph ever created, deals with M87. So here we journey to the heart of the Virgo cluster, to M87. This galaxy certainly is the result of collisions of many galaxies. M87 has the mass of not billions, but trillions of stars. Magnifying the view more from the Pomenis astrograph to the Schulman Telescope shows that there's something remarkable coming out of its core. It is unlike anything else observed in the local universe. This is a relativistic jet of gas and energy that stretches for tens of thousands of light years. Zooming in more with the HST picture shows the detail in the jet and hints at the fact that there is something monstrous, something very powerful in the core of M87 to create this outflow. The only thing known in the universe that can generate this much energy is a black hole. This is what has been assumed, but nary a single example ever directly seen for decades. If you recall, each pixel of HST sees a tiny 0.05 arc seconds of the sky. If we zoom in to just a single pixel in this image, right around the center there, and make it fill 1000 pixels on the screen, then the center pixel is the size of the region captured by the Event Horizon Telescope collaboration. This feat required combining light simultaneously captured from a network of telescopes that span the globe. Nothing less than a telescope effectively the size of the Earth could have enough resolution to capture this region and directly observe the black hole in the heart of M87. This is a mapped or false color image in its displaying light that comes in short radio wavelengths of light that were used in these observations. But before the spring of 2017, pictures of black holes and magical unicorns were in the same category. We live in a time when a century-old question, one for which much ink has been spilled, is answered. Yes, there are black holes in the universe. And yes, much of the physics looks about right. The region shown here is roughly a light day in extent. Recall the penny in our solar system model from earlier. And it has the mass of around 6 billion suns. The image is as fantastic as the object it captures, and it's a first of its kind, a one of a kind, and really an unbelievable astrophotograph to behold. And that is my presentation. You'll see here that it says music. There is no music. You should not have heard music. I use this as kind of a slideshow, but this is a video that I created. You can find it on my YouTube channel. It does have music when I'm speaking in that rendition of this video. But there you go. So now I'll wait for Nick to come back.
Thank you very much, Adam. That was really interesting. Thank you very much for that presentation. So now I'll throw the floor open to questions. Just having a look at the list of questions that we've got. So at the moment, nobody's asking any questions, so I'll take the.
Did I not predict that?
You
Nick?
did. You did predict it.
I don't leave a whole lot of room, do I?
I'm sure there will be some in a minute. I'd just like to ask a couple, really. Sure. First one is, you mentioned early on diffraction spikes.
Yes.
And I know some people actually find those really enhance an image. I got the impression from you that maybe you think that they don't, but some people
let me just say that one of the nice things, there are pros and cons. I think that in terms of public outreach, they're detrimental because people believe that is actually how stars appear. And in that sense, I'm downplaying them. But one of the nice things about diffraction in general is that it spreads the light out and it makes it easier to see the colors of things. So people that use refractors, for example, will often put strings in front of the objective to produce diffraction so that it's easier to see the colors of stars. Yeah.
That's good. And you also mentioned about processing images, and I wonder if you'd just like to say something about the techniques that you actually use. So,
quite a few.
Not going into too much detail, but just tell us a little bit about.
Well, I tell you what I'll do. Let me point at some images. I think that'll make life a little bit easier. So I have 2 web pages that I maintain. For those that are interested in pretty pictures, if you'd like to follow me, you'll find that I regularly post new images that I've processed of space coming from various sources, and this is where you'll find them. For those that are the more advanced and you're interested not in seeing my pictures, but actually making your own, I do create tutorials that explain in infinite detail how to make these images and what is required to kind of make it go, using very particular kinds of software to do that. So to answer the question, let me say, let's see. I will show you an image that, all my new images are here at the bottom. So for example, I'm going to pick one, this. This is really cool. So, you know, an image like this is not the kind of thing that might excite everyone that likes big, bright colors and bold contrast and detail and things like that. This is a very subtle kind of thing. But to me, it's just really remarkable. So here we have the collision of two galaxies. But in order to make this image work, I had to apply very particular kind of processing choices. One of which is that, and a lot of it is actually beyond my control in this case, this is extremely faint. So I have to do everything I can to make sure that the image isn't noisy. So there are certain kinds of noise reduction processing that I'm going to employ that'll make it easier or better to see, you know, these very faint structures. There's a shell here, there's an even fainter shell surrounding that. And then of course, there's this weird outflow of stars being ejected from these two galaxies. But also the galaxies have some internal structure as well. I don't know if I have a larger, let me see if I have a larger image here. Click the image above. No, this is the full frame. Yeah, this is just the full image. But in order to make sure that all of these galaxies, they don't just look like little blobs, but they each have some internal structure, you want to be able to apply certain kinds of nonlinear adjustments as well to be able to display all of that at the same time. So I'm using a program called PixInsight, and it has a very particular a process or algorithm that's useful to do that. It's called, you know, HDRMT. It has a longer name if you spell it all out. Let me show you another image. Sorry to get you dizzy there looking at all these crazy images. Here is an image of something that, again, that HDRMT was really necessary. Maybe I even have a higher, yeah, I do. There we go. So this is a nebula that I suspect most of you have not seen before. This is something that excites me, is to take pictures of things where there may not exist. You can look in a book, in a magazine, you can look anywhere you'd like. I don't think you're going to see a nice high resolution picture of this field. And I think it's fascinating. And in order to really see what's going on in this field has a very dark nebula. It's extremely dark. It looks bright here, but it's not. So I had to take very long exposures to get enough data so that I could brighten the image. But in the process of doing so, everything surrounding these interesting stars, which are lighting it up, they become very difficult to manage, to be sure that it has the color and it looks natural kind of in its environment. So that combination of noise reduction, as well as the nonlinear adjustments that are being made, all go into what I think makes an image like this look natural, but it is far from natural if you were to actually look at the image processing choices that I made when I did it.
Thank you. That's a really good answer.
Probably a very verbose one. Sorry.
No, they're really good and they're excellent images. So there are a couple of questions now. So I'll go through them in reverse order. So Callum Potter asked an interesting question, which I think you've kind of almost answered in what you've just said, which is, when you go imaging, how do you decide what you're actually going to image that night?
Yeah. So there are lots of pictures of things. Let me show you another example because they just excite me. It so happens that some of what I think are the best pictures I've ever taken are of these little tiny dusty things because they have structure that's just so unusual. What the heck is this thing? So I often scan, you know, what are the surveys like the Digital Sky Survey and other things, looking for the faint little wisps of something that could be something interesting, but perhaps no one would be crazy enough to spend, you know, some crazy number of hours to get enough data to display it. This is an example, this image is an example of exactly that type, where again, you have this, these young stars that are just being born here from their natal clouds of dust and gas. If you look at, and I guess I can demonstrate this for you, V1025, I'm sharing screen so I can show you everything.
Yeah. So
there is a very nice tool which is called the Aladdin Sky Atlas. It's online. And then I can type V1025. I think this works. No. what is the other name for this thing? This is the problem when you take pictures of these things. They don't have nice names. It is called, I probably have to put Tori. I probably have to add the word Tori. How about that?
Aha. Yeah.
So this got me excited. Look at that. Mm-hmm. Now, who in their right mind would decide, oh, that's a field that I want to take a picture of, right? Now you can, let's see, you can stretch the image. I'm trying, there it is. So you can stretch the image so that you see this, but even in these, old survey type images, digitized images, it still doesn't necessarily look, is that really worth spending that much time on? And of course, I claim the answer is yes. I'm willing to take that risk and go off the beaten path. So that's how I choose. I choose objects because they're big, they're bright, they're bold. Sometimes if it's something like, that already has a wonderful image, how can you improve on it? A good example of that might be the silliest thing, like, again, Betelgeuse here. Who in their right mind would spend, what did I do here? I spent, 1.5 hours in each color just staring at one of the brightest stars in the sky. But I had some suggestions that that field was not just some bland field. Of course, all of the bright stars have in the foreground and background perhaps other interesting things. And I thought that that added a perspective that's not often shown. So that's something else that interests me, is to offer perspectives that either say something interesting about the universe, or perhaps a way to look at things in a different way, literally in a different light.
That's great. Thank you very much. So we've got a few more questions now. So I'll ask, David Arditi's asked a question. He says, do you usually use remote telescopes, or do you take your equipment to dark skies, or do you sometimes take your images from home? If so, what's your sky like?
So being in Arizona and having literally, I developed the program at Kitt Peak for the public outreach there. This was back in the 90s and into the early part of the century. And then I went on to found the Mount Lemmon Sky Center, which is part of the University of Arizona, now a destination you can visit on top of Mount Lemmon, just north of Tucson. In all of these cases, I was fortunate enough, through the help of many people, to get telescopes and incorporate them into my job. So the funny thing is, I actually don't have any big, nice telescopes of my own, because I've made it my livelihood to, in some way, associate myself with telescopes that others have, I guess. So I'm a little bit of an astro leech, but I hope I make up for it in some way. So yeah, but what I was going to show you is my attempt from Arizona. Now, you guys had a much better view of this than I did. In Arizona, it was the monsoon season and it was very low in the sky. But I did this on my own by going out. I had to drive basically 3 hours away to get away from the Phoenix lights and to get away from the monsoon storms and everything, to get this is my only picture of, nice picture of Neowise.
Very
so
nice.
There, I did something on with my own equipment.
Very nice picture indeed, and it was a very nice comet, and we've spoken about that.
I mean, it was circumpolar for you guys. Jeez.
It was, although it was right in the middle of the summer, so it was at that time when certain parts of the country it didn't actually get that dark, but it was very nice, and that's a really nice picture as well, showing the details in the tails there.
Yeah, the synchronic banding.
Yeah, that's grand. So Nick Hewitt has asked a question, which after all of these lovely color images we've seen, he's asked the question, is there much of a place for monochrome images these days?
Well, look what I'm showing here. Although it's not technically monochrome, the solar corona itself doesn't have that much color. You can kind of see some little flare things there. But yeah, monochrome offers a different kind of perspective because it makes you look at an image in a different way. You really are more, I think, cognizant of contrast and detail, something that our eyes are particularly, eye and brain are particularly well suited to do. Sometimes with the addition of color, it adds yet another dimension that can change the way an image feels or what it communicates just by that extra complexity. And I think, for example, Ansel Adams would agree with me in that assessment.
Mm-hmm.
So he might say that grayscale images, in some sense, are a simplification that can give them a larger voice. So I think there's a place for it, but I don't mind the complexity that color gives. And I do, of course, think that when you add color to images, it does provide more information. And that extra information can really say something very interesting about perhaps something astrophysically or something about something that might be beautiful in some sense.
Mm-hmm. What do you think about narrowband imaging and using palettes like the Hubble palette?
Yeah. So, one of the interesting things is that I have nothing against it. I actually don't have that much experience with it. I blend in, for example, H alpha, and let me show you what that looks like. But I have not done exclusively narrowband mapped color imaging. One of the nice things about doing the mapping is, of course, that, do I have my M1 here somewhere? I must. I don't even know where it is. One of the nice things about doing that mapping is that the contrast of the nebula in its component wavelengths is just so striking. You never get that when you look at a straight up broadband image, which I think actually makes broadband imaging harder at some level to capture sometimes nebula, to really show the contrast of what might be going on, because in many cases it can be just very red. You just don't see an awful lot. But yeah, I certainly love that contrast, and in some sense kind of the depth that narrowband imaging gives, because it allows you to separate different features of nebula. Let me show you, since I mentioned it, my kind of thing with, hold on, narrowband. You won't consider this narrowband, but it is. This is, well, I guess I showed M82 in the other image, but I've blended in here the hydrogen alpha information to really make the filamentary structure of the Crab Nebula stand out more. It's not that there's plenty of red in the nebula. I didn't need it to necessarily, I don't want it to overwhelm the picture. I just want it just to bring up the filamentary structure, because I also want to see the structures that show up in the blues and the greens here, as well as the red. If I just brought in a lot of HA, all of that goes away.
That's good, thanks. So we're coming up to 8. There's just one last question, which is actually very relevant. And okay. I don't know what the situation is with you in Arizona, but we have quite a lot of restrictions on public meetings and things here in the UK because of the COVID. Right. And this is a question from James Gage. He says, how are you adapting your outreach programs to the current situation?
Right. So first thing is, at the moment, I'm not managing the Sky Center. It continues to do its programming, though right now you've correctly identified that public programming is not possible, because the whole idea is to invite people to come up to visit the telescope and look through the telescope and interact very closely and intimately with everyone else. So not doing that at the moment. The facilities as far as public outreach are still available to log on to, if you want to take advantage of the telescope. I would encourage you to visit the Sky Center website, skycenter.arizona.edu, and you can read more about how to do that. But as far as the public programming, it is paused until things improve publicly to allow those kinds of interactions again. I don't know when that's going to happen. That is, this is a strange, wow. It's like in the movies, right?
It is.
Crazy.
And I guess we none of us really know when it's going to come to an end. But yeah. It has had some positives, and I think things like this, where we can actually have people from far away like yourself spending their time presenting to us, is something that's a real improvement over what it used to be. So thank you very much, Adam. Thank you very much for your time.
Sure. Thank you for inviting me.
You're very welcome, and hopefully we'll have you back on again sometime. I think everybody's various comments say how much they've enjoyed this.
Oh, great.
So thank you very much.
All right.
Go and enjoy the rest of your day.
And have a good night.
Thank you very much.
All right.
Cheers.
Cheers.